So the next example is that defined on the Galois group, which is defined over Q, where 2 to the power 1 by 3 has been adjoined to this Q, which is defined over this field of rational numbers. So that means we have the lower field as the field of rational numbers, and we have the higher field as this field of rational numbers where 2 to the power 1 by 3 has been adjoined to it. So this is given to us. So that means this is our F and this is our extension field E. So now the minimal polynomial, because this element has been adjoined to this, therefore the minimal polynomial of 2 to the power 1 by 3 over Q is x cube minus 2, because when you substitute x is equal to 2 to the power 1 by 3 and when you cube both sides, so you will have this. So you would have this as the minimal polynomial for this particular element. Okay, so this is the minimal polynomial of the element 2 to the power 1 by 3 over Q. Therefore, what would be the degree? Therefore, the degree of the polynomial, this field Q 2 to the power 1 by 3 over Q, that would be equal to the degree of this minimal polynomial, and which is equal to 3. So this is the degree. Next, what would be the basis of Q, where 2 to the power 1 by 3 is defined as a vector space over Q. Its basis would be 1, 2 to the power 1 by 3 and 2 to the power 2 by 3. So this is the basis, because if you have some element u as here and its minimal polynomial has degree n, then the basis set would have 1 u up to un minus 1 element. So here the degree is how much? 3, and you have u as 2 to the power 1 by 3. So we'll go from 1, 2 to the power 1 by 3, 2 to the power 2 by 3 and until here only, right? Okay. So this is the basis. So now what we do, we take some element sigma or some mapping sigma. Let sigma belongs to G be the automorphism. Then sigma is the unique linear combination of the elements of the basis. So that means you could write sigma as A plus B alpha plus C alpha square. That means the linear combination. And what would be this? Sigma of A plus sigma of B sigma of alpha plus sigma of C sigma of alpha whole square. Now this would be equal to A plus B into sigma alpha plus C into sigma alpha whole square. Why? Because all the elements A, B and C, they belongs to this lower field Q. So that means sigma of A would be equal to A, sigma of B would be equal to B and sigma of C would be equal to C. So this is what we would have. Okay. So what would be alpha of sigma of alpha cube? So this would be equal to sigma of alpha cube. And what is alpha cube? Your alpha was 2 to the power 1 by 3. So what your alpha cube, that would be equal to 2. So it would be equal to sigma of 2. And what is sigma of 2? Because 2 belongs to this Q, that means sigma of 2 would be equal to 2. So from here we have sigma of 2 is equal to 2. So you could write this to be sigma of alpha raised to power 3, that is equal to 2. Or in other words, what would be sigma of alpha? It would be 2 to the power 1 by 3. So that means we have calculated this sigma of alpha from here, which was not available from here. So that means you could now write sigma of alpha. This would be 2 to the power 1 by 3. So what are the roots of, cube roots of unity? They are 1, omega and omega square. So that means what is this 2 to the power 1 by 3? That is 2 to the power 1 by 3, 2 to the power 1 by 3 into omega, and 2 to the power 1 by 3 into omega square, and moreover this omega cube, that is equal to 1. But this sigma of omega that belongs to q 2 to the power 1 by 3, therefore it is real, and the real cube root of unity out of these three numbers, this omega that contains iota, so this is an imaginary number, cube root of unity. So the only real number is 2 to the power 1 by 3, therefore we only have sigma of alpha is equal to alpha, because this is the only real cube root of 2. Therefore, the mapping sigma is an identity mapping. Therefore, we say the mapping is trivial mapping. So, this group of automorphisms for this field Q, where 2 to the power 1 by 3 has been adjoined to this Q, is trivial. So that means it is same as the lower field. And so what would be the order of this group G? So its order would be 1, which is quite less than 3. And what was 3? 3 was the degree of Q, where 2 to the power 1 by 3 has been adjoined to this field of rationals over Q. So that means the group of G would be less than the degree of 2 to the power 1 by 3 over Q. And this we will see in general in the next theorem, which says that from here we obtain that in general the order of G defined for E by F, the group of automorphisms, is always less than equal to the degree of the extension field E over F. How this is true? We will see this in the next theorem. Let us just define the statement of theorem, which says that let E be the finite separable extension of field F, then the order of G defined of E over F is always less than equal to the degree of E over F. So this is the statement of the theorem, which we shall prove later on. So I hope this is clear to you all.